Unit the design of a slab. Welcome to the next topic. The topic is design of slabs and the staircase. So first we have to see the introduction of the topic. So reinforced concrete solid slabs are continuous one of the following ways. So that is one is a one-way slab and a two-way slab, a flat slab and a flat plates. So one-way slab is nothing but those supported continuous are two opposite sides so that the legs are carried along one direction. Uh, the direction in which the load is carried in the one-way slab is called the span. It may be in the long or short direction. One-way slabs are usually made to span in the shorter direction since the corresponding bending moment and shear force are least. The main reinforcement are provided in the span direction. Steel is also provided in the transverse direction to distribute any unevens that may occur in loading for temperature and the shrinkage effects in the direction. This steel is called distribution. The steel or secondary reinforcement. The main steel is calculated from the bending moment consideration, and under no circumference should it be less than minimum specified by the code. The secondary reinforcement provided is usually the minimum specified by the code for such reinforcement. Two-way slabs are those slabs that are supported continuously in all four sides and are such dimension that the loads are carried to the supports along the both direction. Flat slab and flat plates are those multi-span slabs which is directly restore columns without beams. Flat slab differ from flat plate in that they have either drop panels, increased thickness of slab, or column capitals. In the regions of the column, flat plates have uniform slab thickness and the high shear resistance around the column are obtained usually by the provision of special reinforcement called the shear head reinforcement placed in the slab around the column. This is the example of the physical example of the slab, that is one-way slab, and next one is two-way slab. This one is flat slab and then flat plate. According to IS 875, the loading on the slabs for buildings are calculated as follows. First one is a self-weight, that is 25 kilonewton per meter cube for a reinforced concrete. Next one is finishes and partitions generally at 1.5 kilonewton per meter square. And third one is characteristic imposed loads as specified depending on the use of the building. For example, for residential and office building, these loads are first one is roofs 1.5 kilonewton per meter square with access 0.75 kilonewton per meter square without access. For floors, 2 kilonewton per meter square for residential, it is for residential, and for office floors that is having 3 kilonewton per meter square. Next one is structural analysis of one-way slab with a UDL using coefficient. One-way slab, because of their one-way slab action, are analyzed as beam of unit width. However, codes allow the use of simple coefficient for calculation of moment and forces in continuous beam and the slabs of the uniform loading with the more or less equal to span and continuous at least three spans. Spans are considered equal if the difference in span are not more than 15% of the larger of the spans. These coefficient for ultimate bending moment and shears are given in the tables 12 to 15 of IS 456. It should not be noted that when using this table, a redistribution of moments between the section is not allowed. And these are the some formulas of bending moment shear force coefficient for the one-way slabs. So note for bending moment, the coefficient is multiplied by the total design load and effective span. According to IS 456 class 22.5, when a member is built into a masonry wall which develops only partial restraint, the members shall be designed to resist a negative moment at the face of the support of WL by 24, where W is the total design load and L is the effective span, or such either restraining moment as may be shown be applicable. For such a condition, shear coefficient given in table 13 and the end of the support may be increased by 0.05. Designed for shear in slabs. Normally, the thickness of the slab is so chosen that the shear can be resisted by the concrete itself, and the slab does not need extra shear reinforcement. It is only in extreme situation where the thickness tends to be very large that shear reinforcement are allowed to be used for slabs. Shear test on the soil slab have shown that when these column shallow members are less than 300 thickness, they have to increased shear resistance, and compared to the members such as beams which are 300 or more depth. This shear enhancement factors for shallow depth is given in table IS 456 class 1 40.211. Shear multiplying factor that is given the below table. For that, overall depth of the slab K is 3000 or more means that the value is 1, and 275 that is equal to 1.05. 250 means 1.10, 225 means 1.15, 200 means 1.25, and 175 means 1.25, and 150 or less means 1.30, where K is called the shear enhancement factor for slabs. According to IS 456, the rules to be followed in the design of the slab for shear are: no shear reinforcement should be provided for slabs less than 200 thickness. However, the increased value of the shear resistance in slab can be taken into the accounting design. It is preferable to design slabs without any extra shear reinforcement. Uh, However, if found necessary means shear reinforcement may be allowed to provide in slabs which are 200 or more in thickness. The spacing of the reinforcement can be increased to D instead of 0.75 D as in beams. In no case, even with the provision of the shear reinforcement, according to IS 456 class 40.2.3.1, should should the maximum shear stress allowed in slabs due to ultimate load exceed one of that allowed in beams as given in table 20 of 2. IS 456. And choosing the span effective depth ratio for slabs, class 24.1 recommended class 24.1 recommended for the following span overall depth factor for two-way slab, that is equal to using for FE 415 up to 3.5 meter span, and the loading class up to 3 kilonewton per meter square. The simply supported two-way slab is nothing but 35 into 3.8 for FE 415 the 0.8 value and 28. Continuous two-way slab is 32 and cantilever slab is 12. For one-way slab, a ratio of 25 and 30 may be more or appropriate. The three rules for choosing steel for slabs are the following class. The diameter of the steel should not exceed 1 by 8 total thickness of the slab. The amount of the steel area is in either direction should not be less than 0.15 percentage of the total areas. When the area, however, this value can be reduced to 0.12 percentage when the high strength deformed bars are used. Spacing of the main steel, that is equal to 300 mm. Secondary steel is nothing but 450 mm. So next we are going to see some problem in slab. Kindly wait for that. The problem is design a simply supported RCC slab for roof of the hall 4 by 10 meter inside dimension with 230 mm of walls around, assuming a live load of 4 kN per meter square and finishes 1 kN per meter square. Use a grade of concrete is 25 and FE from the sheet. First of all, we have to find out it is one-way slab or two-way slab. We have to find out it is a one-way slab and a D value that is equal to 160 mm. Total depth, we have to add the cover value that is 180 mm, and we have to find out total dead load and total load. So and factor design load, effective factor, ultimate moment of shear, and check the depth for check depth for bending and once in the check for depth is working means we have to proceed another step. So and then calculation for shear steel area, main steel of the bar, and provide uh, we have to provide in this problem. We have to provide 10 mm dia bar at 130 mm center to center spacing and check for control cracks control. We have to check minimum steel for slab that is equal to 0.12 percentage, and finally the maximum spacing is 480 mm, and recheck the shear. Once we have to design all the criteria, which means we have to recheck the shear. So in that point value, that is 100 AST by BD into 100 into 604 AST value, and B is nothing but we have to design 1 meter breadth of the beam and 1000 into 160 mm. So finally, it is a slab is safe in shear, and we have to find out slab in deflection. Once we have to check the shear, which means we have to find out the deflection value also. So next one is provide the secondary steel of the beam, and finally the reinforcement details of the one-way slab, and then cross-sectional dimension of the slab. So in this case, we have to see the all the values and the steel bar dimension and the spacing values, etc. So this is the one-way slab problem. Thank you for listening. So we have to update our problems in next video also. Thank you.